Hi, it's Mrs. Moss here, and we're going to continue talking about energy and all the different ways that we use energy. As you can see, I got my rainbow mug here, talking about the electromagnetic spectrum a little bit and all the colors that make up white light. Let's get started. So when we talk about energy, we have to look at the law of conservation of energy, and that states that energy is not created or destroyed. It can only change form. That means we cannot get rid of it completely. It doesn't disappear off the face of the earth. It cannot be created in its own. It can only change forms. Now let's talk about the different forms that we're going to be responsible for in this class. Potential energy, which is the energy of position, P, and it is stored. And that's before it begins to move, it's just in something in place. Kinetic energy is the energy of motion, and the faster movement equals more kinetic energy. So let's get a visual. In this instance, we have three skiers, A, B, and C. So who would have the greatest kinetic energy? Well, knowing that kinetic energy is the energy of movement, B would need to be the one with the most kinetic energy because it's going downhill and it's moving fastest. If we look at these same three skiers and we think about potential energy, we need to decide which one has the greatest potential energy. Well, that would be skier A, because he's not moving yet. He's right teetering on the top, but he hasn't gone down yet. So because he's not moving, that would be considered potential energy. When we talk about kinesthetic energy, we actually are talking about temperature because temperature is a way of measuring the kinetic energy of a substance. Fahrenheit scale and Celsius scale are the two that we look at when we're measuring temperature. The boiling point is at 212 degrees Fahrenheit. The freezing point is at 32 degrees Fahrenheit. However, on the Celsius scale, the boiling point is at 100 degrees and the freezing point is at 0. Now you're going to open up your reference table to page 13, and you can see that there is a thermometer and a scale that measures both Celsius and Fahrenheit. There's a third actual unit of temperature on there as well, and that's known as Kelvin. Now that's measured for very high temperatures such as the sun and energy. But for right now, just look at those over and you can actually practice converting from Celsius into Fahrenheit. During the energy exchanges, one thing is losing energy as the other is gaining energy. So in this instance, the wave is losing its energy and the sand is gaining its energy. As the wave splashes onto the beach, the sand picks up the energy given by the wave. In this instance, energy will flow from the flame to the finger. So you better watch out. Don't play with matches. Now energy will also flow from the finger to the ice, keeping in mind that the finger has more energy, it's warmer, it has a higher kinetic energy, so it will flow into the ice. Now in this instance with your cup and ice inside the cup, the energy will flow from the drink and the liquid to the ice. And that's what causes it to melt because the energy is gaining, the ice is gaining energy from the liquid. So when will the energy exchange stop? When equilibrium is reached. Now you hear the word equal and equilibrium. So when there's a balance between energies, the energy exchange will stop. Now what does this mean? Well, when your drink gets to room temperature, all of the ice had been melted already and it levels off at room temperature, then there will be no more energy exchanging. One is not warmer than the other. One is not filled with kinetic energy than the other, so the energy exchange will stop. That when things are in balance, we consider that an equilibrium. Now, Let's move on a little bit and talk about another way we look at energy, and it's called specific heat. Specific heat is the amount of heat energy needed to raise 1 gram of any substance 1 degrees Celsius. So in other words, it's basically how long it takes for a substance to heat up and cool off. If you look at your reference table, this time on page 1, if you need to pause the video and get it out again, please do. You will find the specific heats of common minerals chart, just as I said on the page 1, the front cover. Now, if you look down the list, liquid water is at the top. And if you see the top of the category where the number 4.18, that stands for joules per gram in degrees Celsius. So that means liquid water has a specific heat of 4 joules, which is a form of energy. It's a unit of energy, and it takes that amount to heat up 1 gram of the substance of liquid water. And going down the list, you see that it gets smaller and smaller as we go down. So liquid water has the highest specific heat, lead has the lowest specific heat. Now, what does this mean? Well, if you were running a race and you had a very high number like liquid water, you would lose because you'd be going slower. Well, that's what happens with this situation as well. Liquid water takes longer to heat up, it takes longer to cool down, so that it has a high specific heat. It has a high number. Lead has a small number. So that means you can heat lead up fast. And once you take that heat off of it, it will cool down equally as fast. And we have other substances in between, and we'll get into a little bit of that in a moment. So the higher the specific heat, the more energy is needed to raise the temperature. It takes longer to warm up. So how does this relate to our Earth? Well, our Earth is made up of basalt and granite primarily. And if you look at their specific heats, they're somewhere in the middle, but relatively speaking, they have a low specific heat. So they are going to cool up and cool off and heat up faster than other substances on our Earth, like liquid water. So in this situation, when we're at the beach and we have an ocean, the land is going to heat up faster during the day and it's going to cool off faster at night. Think about that. When you go down to the beach, you have to wear your flip-flops because the sand is so hot. But if you go to that same beach at night, it's actually, the sand is very cool. It heats up during the day and it cools off at night. The ocean, on the other hand, is different. If you go to the ocean, it's going to remain the same temperature day to day for the most part. When you're in the heat of the summer especially, it's going to keep that heat in there and it's going to hold that heat because liquid water takes a long time to warm up. It also takes a long time to cool off. So that's the end of our energy unit for right now. I'm sorry, not the end of the unit, but the end of this video. We're going to watch another video another night that talks more about transfer of energy and how energy actually does move from one thing to the other. Have a great day. See you next time.